Let's get started. Let's look now at the multiplication and division principle. We've already used this a bit, so this in a way will be a review for you. We see that in addition to having terms added and subtracted to your unknown, you can also have your unknowns multiplied or divided. For example, we could have 4 times the unknown r is equal to 8. Or a more complex case, 3 times the unknown n divided by 5 is equal to 15. We're going to see the kinds of things you can do to be able to solve equations that are like this. Let's talk about the multiplication-division principle of equality. And basically what it says is if you divide or multiply something on the same thing on either side of an equation, you still have an equation when you're done. You're not affecting the mathematical integrity by that operation. For example, here we have 3 times x balancing 12 is equal to 12. If I multiply the 3x by a 5 and the 12 by a 5, I still have an equation when I'm finished with this operation. Similarly, if I have 3x equals 12, if I divide one side by 3 and divide the other side by 3, I can be sure that when I'm done with this operation, that equation sign is still going to be valid. I can still be certain that I haven't violated any mathematical rule and have the same things on both sides. So if the equation had a value of true, if that equation was true when I started, it will also be true when I'm done and, of course, have done all the math right. You always have to be careful about that. Remember now, by way of review, there are 2 things we need to think about when we're solving equations. One is we need to do whatever is mathematically appropriate to get the variable by itself. And while we're in the process of getting that variable by itself, we need to always remember to do the same thing to both sides of the equation. Let's look at an equation. Here is 3 times the unknown n is equal to 12. What must we do to solve this equation? Right. We divide the left-hand side by a 3 because 3 divided by 3 gives me 1n. And if I do it to the left, I also need to do it to the right. What I wind up with now is 3 times the quantity n divided by 3 is equal to 12 divided by 3. I can be very certain that's correct. N divided by 3n divided by 3 is 1n. 12 divided by 3 is equal to 4. 1n is the same as n, so my solution is n is equal to 4. And of course, we can check ourselves by substituting 4 in for n. So 3n is equal to 12. 3 times 4 is equal to 12. And I have done this incredibly difficult problem, and I can say, wow, good job, Dan. Let's look at another one that might be a tiny bit more annoying, but not too much, because now we have to use both principles together. You see, we have constants added to the variable terms. 8r plus 7 is equal to 4r plus 15. Again, the first thing we need to do are those operations which get all of the numbers on one side and any kind of expression involving variables on the other side. So as I look at this, it seems to me that the most logical thing I can do to get the variables on one side and the numbers on the other would be to subtract 7 from each side of that equation. When I do, 7 minus 7 is 0, and I'm left with 8r by itself on the left equal to 4r plus 8. Let's go to a new slide and continue working on this problem. The next thing I need to do to get the r's by itself, see if you can follow with me and stay a step ahead, is I subtract 4 from each side of the equation. When I do that, 4r minus 4r goes to 0, gives me 0. And on the left, I have 8r minus 4r, that's 4r, equals 8. Still not done because I want 1r, not 4 of them. So what I have to do, follow along with me, what do I have to do? Divide both sides of that equation by 4. When I do, I get 1r on the left, 4 divided by 4 is 1, is equal to 8 divided by 4, or 2 on the left. My solution is r equals 2. And of course, I'd like to check this, and I do it by substituting the 2 in for r on both sides of the equation. 8 times 2 is 16, plus 7 is 23. 4 times 2, which I've substituted in for r on the right, is 8, plus 15 is 23. 23, amazingly enough, equals 23, so I can be sure that I've done that equation correctly. Here we go. Here's another example, again, getting more and more and more complex apparently, but what you need to remember is that you're not going to be able to solve very much math beyond simple arithmetic problems in your head. All of these things are multi-step problems, and you need to work them out exactly as I've been doing in this class, a little bit at a time. And as I've been doing here, even though I'm using all this electronic stuff, you can do the same thing on a piece of paper, and you need to do it step by step by step. If we look back at the slide now, you see what I have is something that looks incredibly complicated on the face of it, but if I attack it a little at a time, it will resolve itself into something quite doable. So in this case, I have 6 plus the quantity 3 times the quantity z minus 2 plus 6z is equal to twice the quantity 3z minus 8 plus 22. What I need to do first is get rid of those things I've called the quantity, that stuff inside those brackets. And to do it, I need to use the distributive rule. 3 multiplies both the z and the minus 2 on the left. 2 multiplies the 3z and minus 8 on the right. Let's do that operation. I have the 6, then 3 times z is 3z, 3 times minus 2 is minus 6. Then I have the 6z that was just sitting there. Doing the distributive rule on the right, 2 times 3z is 6z, 2 times minus 8 is minus 16. Then I still have the 22. Now let's clean up a little bit more. I want to keep simplifying. I see I have z's and numbers on the left. Let me put the z's together and the numbers together, and let me simplify plus 22 minus 16 that I have on the right, and I'm left with this. Continuing our simplification, 3z plus 6z, 9z, and plus 6 minus 6 is 0. So I've simplified the equation from that fairly complex looking thing up on the top to 9z equals 6z plus 6. Now remember, my next strategy is to get z's by itself on one side or the other. Let's do this. Let's get all the z's on the left by subtracting a minus 6z from both sides of this equation. Having done this, I see I have 3 times z is equal to 6, and I'm one step away from finishing. In order to get z by itself, since I have z multiplied by 3, I need to divide the 3z by 3, but if I do it on the left, I must also do it on the right. And I wind up with the solution to the equation that z is equal to 2. Before I can go on, of course, I would like to check to see if my answer is correct, if my solution is correct. So wherever I see a z in the original equation, I substitute a 2. So I have 6 plus 3 times 2 minus 2, very nice, that goes away, plus 6 times 2 is equal to 2 times the quantity, 3 times 2, 6, minus 8, plus 22. Continuing with the math, I get 6 plus 12, that 3 times 0 goes away, is equal to twice the quantity, 6 minus 8 plus 22. We continue working on this, and 6 plus 12 is 18 on the left. 6 minus 8 in those brackets is minus 2, and I'm left with that. And I see right away at this point, 2 minus 2 is minus 4, so I have 18 on the left, equal to minus 4 plus 22 from the right. That's equal to 18. 18 equals 18. I've substituted that correctly, so I can pat myself on the back and say, good job, you've done it again, you're very smart. And after you practice this for a while, and you do about 1,000,000 of these, well, I'm exaggerating a little. We saw in one of the earliest units what 1,000,000 might be like, but if you do a few dozen of these, actually, you're going to have the hang of doing it down pretty well. Actually, you know, when you see an equation, most people don't have a lot of trouble starting with an equation and then following through the steps that let you get to the solution. That's fairly mechanical. Where a lot of us have problems is taking something that's written out in words and then moving from the description in words to the math. And then once you have the equation written down, again, you follow these kinds of principles that we've been talking about already. Let's look at now what we need to do to translate words to equations. What looks like one of my teachers on the left over there goes 3 plus, and of course there's me possibly without the beard. People haven't seen me without my beard for quite a while, thinking about how to do a translation from English to math, and that's what we're going to look at in this section of Unit C. When you have addition, for example, x plus 3, let's look at the way you can say that in English. You certainly can say x plus 3 and see that written out. What other ways? 3 added to x translates to x plus 3. 3 more than x, same translation from English to math. The sum, remember that the sum means what you get when you add stuff up. The sum of x and 3 also means x plus 3. X increased by 3. In other words, x is made greater by adding 3 to it. X plus 3. Now remember that x plus 3 is the same as 3 plus x, so that if you say that backwards, you still mean the same thing. X plus 3 is the same as 3 plus x. 3 added to x is the same as x added to 3. You might swap it around, but mathematically you're going to say absolutely the same thing. What about subtraction? X minus 3, which is the most direct way to translate subtraction. 3 less than x. Again, 3 less than x means take 3 away from x. 3 subtracted from x, x minus 3. X decreased by 3 as opposed to when you had x plus 3, it was x increased by 3. X decreased means you're taking stuff away, therefore you're subtracting. And another common one is the difference between x and 3. Subtraction can be used to establish a difference. If I ask what's the difference in temperature between now and the previous night, you would take the higher temperature and subtract the lower temperature, and that would give me the difference between those two temperatures. Difference is an important indicator. That word difference is an important indicator of subtraction. Now, unlike addition, subtraction matters in terms of the order. If you have x minus 3, it's not the same as 3 minus x. You have to be careful about that because, for example, if you had 3 minus x, you would have x less than 3, not 3 less than x. So that you cannot just flip them around the way you could for addition. For subtraction, we have to translate those phrases exactly as they're given in the English, or you could wind up with something that's negative of what you actually want. And then when you put that into an equation, you'll find out when you get your paper back that you don't have it correct. So you need to be careful about subtraction and division are two things that can't be swapped around. We'll talk about that too. So if I have x minus 3, it's not the same as 3 minus x, and so forth down that list of subtraction phrases, or phrases that would let you indicate to you that you should change something to a subtraction. Now let's look at multiplication. For example, 3x. How would you say that? 3 times x is one way. X multiplied by 3, fairly straightforward. Remember the word product? It's what you get when you multiply things. We could say the product of x and 3. All of these phrases would indicate that you need to multiply something by something else. Like addition, remember that multiplication is shorthand for addition actually. It's commutative. 3x is the same as x times 3, and you don't usually see x3 around. It's mathematically correct, if not a little bit confusing. Again, you can state things either way with multiplication. 3 times x is the same as x times 3. X multiplied by 3, the same as 3 multiplied by x, and so forth. What other additional expressions could we use with multiplication? A few colloquial expressions, or double, twice, 2x, triple, 3x, quadruple, 4x, and there are others, but they're less often used. Now, division is related to subtraction. So, of course, one way to translate this, the most direct way, is x divided by 3. 3 into x, the quotient. Quotient is what you get when you do a division, the quotient of x and 3. 3 divided into x, and the ratio of x to 3, and we'll be looking at ratios in a later chapter. You can't reverse the order. It matters. You have to translate these phrases exactly the way they're given. The equal sign, that also translates to and from language. Equals, of course, is the most direct way, is the same as, and just the plain old is, all indicate that you should have an equal sign. Powers and exponents, x squared, the square of x, x cubed, the cube of x. Going in the other direction, suppose we have higher powers, x to the nth power, where n could be 5 or 6. So I could say x to the 6th power, or x raised to the 6th power. Square roots. The square root of x is how I would translate that set of symbols. And you can actually have, if you have x cubed, you can also talk about cube roots, where n would be 3. In later math courses, we'll be looking at the things like the cube root or fourth root of x. Not in this one. How do you talk about parentheses? You can talk about 5 times the quantity, 5 multiplied by s plus 3. 5 times the quantity. And when you say quantity, that's the magic word for brackets. Quantity, brackets, bam, you got it. So that's how we would translate that. Well, let's see if we can put our dictionary into words, and we'll start simple and work our way up to things that might not be quite so immediately obvious. 5 more than a number equals 8. 5 more than, that tells me I add 5 to a number, let's call that my variable, equals 8. 5 more than, 5 plus, a number, n, equals 8. We're in good shape. Now let's solve this. We get n alone by subtracting 5 from each side of the equation, and we find that n is equal to 3. And of course we can check by putting the 3 in, and we see 8 equals 8. Let's look at another one of these examples. A number increased by 8 is the same as twice the number decreased by 2. Let's see if we can pick this one apart. A number, z, we'll just call the number z, increased by 8. We add 8 to it. Is the same as, that's the equal sign, twice the number decreased by 2. There's the twice the number decreased by 2. Now we have our equation translated from the English, and we can go through and solve this equation. Z plus 8 equals 2z minus 2. What's the first thing you would do here? Let's get the z's together, and let's subtract a z from both sides of that equation. So I'm left with 8 is equal to z minus 2. Now let's add 2 to both sides of the equation, and we're finished. We get 10 is equal to z, and we can check to see if this is correct. If we put in our original equation, wherever we had a z, we put a 10, we see we have 18 equals 18, and we're good for this equation. Let's look at another one. 53 less 5 times the difference between a number and 5 equals negative 2. This looks a little more awe-inspiring. Let's see if we can pick it apart. 53 less 5 times the difference between a number and 5. So we have 5 times something, and whenever you have 5 times what seems to be some quantity, you're talking about a bracket dealie. So 5 times the difference between a number and 5, the difference again indicating subtraction, equals, very straight translation there, negative 2. Negative 2. There is our equation. Now we need to solve it. I see that I have brackets that I need to get rid of, so I need to distribute that minus 5 over the x and the minus 5. When I do that, I multiply minus 5 by each of those terms. Minus 5 times x is minus 5x. Minus times minus 5 times minus 5 is minus times minus is plus 25. I simplify by seeing that I have one unknown on the left and 2 numbers. I add those numbers together. Then I subtract a minus 78 from both sides and wind up with minus 5x equals minus 80, where I run out of room. So you should do the same thing. You grab a new piece of paper, start at the top, and at this point I see that I need to divide both sides by minus 5. I do that, and I wind up with x equals 16. To check, I put the 16 in wherever there was an x, and I do the math. I have 53 minus 55 minus 2 equals minus 2, and I see I'm in good shape here. I'm going to try one right now that is a little bit beyond what I told you I would do. We said that we would deal mostly with linear equations. I'm going to do one that has a squared term in it just to show you how it works, and we'll go through it quickly. We don't need to dwell on it. Let's look at it though. 1 more than twice a number added to 8 gives the same result as squaring 1 plus the number. 1 more than twice a number added to 8, twice the number added to 8, 1 more than twice a number added to 8 gives me equals the same as squaring, there's the square, 1 plus the number. Let's see if we can solve that. I need to square the number. Remember how to do a number squared. It's the square of the first and last term, then twice the product of the first and last term. Now I have to solve this by getting n's and so forth. I see I have a 2n on both sides, so that amazingly enough subtracts out. I have a 1 on both sides. I can subtract that out, and I wind up with n squared is equal to 16. What times itself will give me 16? The answer is plus or minus 4. I did this one quickly just to show you how a translation like this would work that's fairly complex. Typically, you won't get anything at this level of algebra that's quite this horrific, but I just wanted you to see it done.